All right. Hey, class. All right. And Mr. Bean here. Okay, so we're going to go over Lab 39. This is friction, the virtual portion here. And we want to just give a little theory and background on what you guys are going to be doing today. So basically, friction involves two surfaces, okay? And you have to have motion. So if the motion is in this direction, okay, you have surface one here and you have surface two. So friction is when two surfaces pass each other, you create like a little force here, and that's called friction. So friction opposes motion. At the microscopic level, if you look closely here, you see that there's uneven edges here on the surfaces here. And so what's happening is that these crevices or little cracks here create little friction or create opposition, or you have to move past these. So these little micro wells and bumps is what's creating friction. Okay, and here's another example of that. Let me go ahead and click on this simulation here, and we'll take a look at this. Okay, so here we have two surfaces. We have chemistry and physics here. So we have a book here. I'm going to put the book closer, and notice there's a thermometer here. Okay, now this is like rubbing your hands together. It produces heat or kinetic energy. So I'm going right here. I'm rubbing back and forth, and notice here you have heat being generated. Okay. This is supposed to represent molecules or electrons, if you will. So really, because of electrostatic repulsive force, you really never touch anything. So technically, when you hit someone, you're not really touching them. However, the electrostatic repulsive force is what's causing the injuries and stuff. Okay, so friction is opposing to a motion here, generating heat. Okay, all right, okay, all right. Now with the lab here. Okay, so friction, okay, depends on, let me get a drawing here, depends on two surfaces. Okay, so two surfaces moving past each other, moving past each other. Okay, all right. And you've got a stylist here. Okay, each other. Okay, so that's what friction is. Okay, now, there's an equation here that says friction is equal to what's called this coefficient here, and this is called a normal force. Now, usually we're probably used to seeing something like this. Here's force here, and I'm going to put a little f here to mean that this is friction force. Okay, frictional force here. Now, it equals this thing called mu, not to be confused with meow. Okay, it's mu, and of course here we have the normal force. Okay, now, okay, so again, if I go here, here's the force of friction. Okay, and this is mu. Okay, not meow, and normal force is just simply mg. Okay, now it's mg if we're on a flat surface. Okay, if we're on a flat surface, right? If we're on a flat surface here, okay, if I'm right here and I'm moving something like this, right? Okay, now technically you could say it's cosine of theta. Okay, you could say that. Now, if I'm here, theta when it's flat is zero, right? Theta is zero. Okay, when it's flat surface. So theta, cosine of zero is what? Ah, one. Okay, sine of zero is one. Hey, sine of zero is zero. So cosine of zero is one. So it's just mg. But when we're on an inclined plane, now luckily we won't do any inclined planes until next week. If we're on an inclined plane like this, right? Here's theta here, right? Okay. Now on an inclined plane here, remember this force is always the parallel force, right? This is the parallel force, okay? And this is what, mg sine of theta, right? In fact, we're going to discuss this next week. We don't have to worry about this right now. Okay, so we'll just worry about flat surfaces for right now. Okay, flat surfaces. All right. Okay. All right. So now, okay. Now there's two kinds of friction. Actually, there's three, but there's two kinds. Okay, so let me go ahead and write this out real quick here. So here's force is equal to this mu, right? And it's mg. Okay. All right. Okay. Now this mu value, it has a range of values here. Okay. Okay. Mu can range from 0 to 1. Okay. So it can range from 0 to 1. Zero is kind of like, can you imagine throwing oil on ice? Okay, okay. Is that pretty slippery? More slippery? Okay. So you get towards zero, it means frictionless or oil on ice. Okay. Now, one, as we get closer to one, what do you think one is like? Lots of friction? Okay. How about sandpaper on sandpaper? So we could say sandpaper, right? Sandpaper, right? On sandpaper. So sandpaper on sand. Oh yeah, actually we can. Next week you will actually do, I have sandpaper. You try to rub it. It's really difficult. I mean it's tough. Okay. So sandpaper on sandpaper. Okay, that's good. Now sometimes people ask, what about greater than one? If something's bigger than one, like 1.3, 1.4, now we're talking about adhesive forces like tape, duct tape, and stuff like that. So we will only worry about between 0 and 1. Okay. Now, take a look at this equation right here. This is the force of friction. Okay. Now, has anyone ever been stuck in the snow in a car and your car spins? Okay. Now, think about this. Okay. What's one way you might be able to increase your force of friction if you're on ice or a slippery surface? Yeah, good job. So, like in a pickup truck, you add more people to the car or add more weight. Absolutely, absolutely. That's one way. So there you're affecting the mass, right? You're changing the mass there in this equation, right? You're increasing the mass by adding more weight and stuff, right? Now, there's another way too. You're going to affect the mu. So whenever you go to like a store or out here, when there's ice on the floor, can you throw sand on it? Okay, you ever see like on Mount Rose Highway or somewhere or Highway 50 when it's snowing, a big truck, dump truck comes by and it drops sand on the road? So if I drop sand on the road, I'm changing the mu, the coefficient of making it higher. So there's more friction. So you can change the mu by adding sand. Okay. So like for example, if I add sand, right? Okay, add sand, you're increasing the mu. Okay. Could you wear cleats on your shoes? Okay, so like rubbers, like basketball. If you wear a slick soles, or wear rubber soles, you're in the gym. Which one you have better traction? Yeah, the rubber. Yeah, yeah. Okay, the rubber. Yeah, absolutely. So it also depends on what kind of surfaces you're dealing with too, as well. Okay. All right. Okay, everyone's kind of cool with this, or okay, all right. Now, before we get to this virtual part here, now there's two kinds of mu's. Okay, let me go over here. Okay, there's mu, what's called static, and there's mu, what we call kinetic. Okay, so this is static. Okay, okay. Now, if something's static, what does static mean? Is it moving or not moving? Yeah, not moving. If this is kinetic, kinetic means what? Moving. All right. Now, before we start here, anyone here move furniture in their house or your bedroom? Moving a shelf or a dresser? Which is easier, to get it started moving or have it moving or keep it moving while it's already in motion? Okay, which is harder generally? To start it moving? Okay, that's because static friction is usually greater than kinetic friction. So what happens is that you have friction here. Okay, now this is friction. I'm going to put little s here for static. Okay, that means not moving. Okay, equals, this is going to be mu static mg. Okay, so this is for static friction when something's not moving. Okay, and we'll talk about that here in a second. And here is friction, force of friction. We'll say kinetic. Okay, that means when it's moving. Okay, so here we have mu kinetic times mg. Okay, now I'm going to go ahead and pause the video here real quick. All right, so now we come down here. I want to look at this virtual lab. Okay, so everyone's going to come to this lab here, and we're going to hit begin. Now, each people have different surfaces. Okay, so if you're working in a group of two, make sure you're not copying off your friend because everybody has different surfaces. So, for example, type of surfaces: rubber on ice, aluminum on steel, glass on glass, graphite on graphite. rubber on concrete, wood on table. So it doesn't matter what combination you have, it's this procedure is the same. Okay, however, you will have different calculated values. So you want to be careful. Okay. So what's going to happen is that, so here you have this surface here, right? And you can change the mass of it, 301 grams or, whatever the case may be here. So what happens is that we're going to have a sensor here. Now, this is a veneer sensor. We're going to use our Pasco sensors, okay, to pull it. We're going to use a force sensor, okay? So what's going to happen is that you have a here. So we're going to do this virtually. Next week, we'll do this for real, okay? So I'm going to go ahead and click start. So you're pulling on it, generating force, static. Now it's, okay, you see how it right to right? Okay, it moves. All right. So now you're going to get a graph that looks like this, okay? Next week, you're going to have to make this graph by yourself in front of me, okay, for real. Graph just like this, okay? All right. Now, take a look here. Okay, this is force. Over here is time, over here, right? Now, take a look at this region right here. Okay, now let me go ahead and go back to the template here. So here's the example here. We have surface 1 on surface 2. Okay, what's the mass of the object? 200 grams. Okay, in this example here, 280 grams, right? Make sure we change this to kilograms. 0.280 kilograms, right? Okay, good. All right. All right, now take a look at this here. Take a look at this part here. Okay, this is called the static region. This is when it was not moving. Static region goes from here all the way to here. Okay, this is when it was not moving. Now, you guys see this top point right here? That's the maximum. Okay, so take a look at that, and I'm going to go ahead and kind of go all the way over here. Okay, what do you think that is? That last peak there, about 0.3, about 0.33. Okay, so 0.33 is what this maximum peak is right here. Okay, so that's going to be the force of friction, static. Okay, whatever this peak is, that's the value. So the force of friction static is going to be 0.33 newtons. Okay, everyone's cool with that? Okay, 0.33 newtons, right? Okay. Now, if this is the static region, what do you think this region here is? Kinetic region. Yeah, you're right. No, you're right. Yeah, it was friction. You're right, but it's kinetic. Okay, this is moving. Kinetic. Okay. Now, is a kinetic less than the static? All right. Now, see how all these numbers are like this here? Now, if I was doing the Pascal sensor, I would highlight all this and take the average. However, I don't have it, so I need to imagine a ruler going through the center. Okay, can you imagine a ruler going through the center? In fact, you can probably have a straight edge. Take a ruler going through the center, and let's see where it adds up. So imagine a ruler going through the middle, and what do you think it's going to be? About 0.22? About 0.21? Okay. So 0.21. Everybody know where this 0.21 came from? It came from right here, the average of this, right? The average. Okay. So 0.21 newtons. Okay, that's what this is. So here's the static friction, which is 0.33, and here's the kinetic friction, 0.21. So considerable difference, right? Okay. All right. Now we need to calculate mu. Okay. So how do we do that? So we have here force of friction, right, is equal to, or excuse me here, friction, right, is equal to mu mg. Okay. Can I solve for mu here? Okay. Mu is going to be whatever the force of friction is static divided by mg. Okay, the normal force. Okay. So in our example here, what's static force? 0.33? Okay. 0.33. Good. Divided by, what was the mass of our block there? Yeah, 0.28. Okay, good. 0.280. Yeah, you're right. You got it. 0.280 times 9.8. Okay. All right, so I think this is within everybody's skill set. Okay, if you can do the sine and cosine and unit circle, and so you can definitely do this. Okay, all right, so 0.33 divided by 0.28 times 9.8 equals about 0.12. So about 0.12. Okay, I think this is rubber on ice. So it's okay. So that's the coefficient of static friction. Okay, coefficient of static friction. Over here, we have to do kinetic. Okay, so same thing. Force here of, excuse me, force of friction, uh, force of friction, kinetic. God, gee, okay, okay, time out. Let me erase it. Okay, all right, hold on. Ah, okay, erase that. Okay, so it's going to be the force of friction here, kinetic, divided by mg. Okay, so force of friction, kinetic, what, 0.21? 0.21 divided by the mass, 0.280, right? 0.28 times 9.8. Okay, so mu kinetic. Okay, so 0.21, right? Divided by 0.28 times 9.8. Okay, so about 0.0 what 8. All right. All right. So this is the coefficient of friction, kinetic, and this over here is a coefficient of friction, static. Okay. So static is greater than kinetic. Okay. All right. That's pretty much it. So each person has a different combination. You have to do two of these. Okay. Just do the calculation here. And then there's some questions at the back here. Okay. Make sure you, because about 5 questions here. So all this should be completed probably by 10:15. Okay. Or so. Okay. Get it done, turn it in, and then work on any outstanding assignments that you have. Make sure you turn the lab in from last class today. Okay. All right. Any questions? All right. We'll hit stop sharing.